the backbone of our nuclear physics program here at NC State. It's a consortium of the three universities, Duke, Chapel Hill, and NC State. And it was realized back then that the three, if I could coin a phrase, the three universities had a critical mass of faculty, and that if they joined forces, they could establish a world-class laboratory, as indeed Tunnel is and has been for many years. And a number of our faculty still work at Tunnel, and Professor Seagondollar was in the ground floor of that. He also was head of the department. Dick, can you tell me when he began as head of the department? 65, okay. So in 1965, he became head of the department and was for many years. And I overlapped him quite a few years. He retired, as I said, in the 80s. And we all know him as not only as a very good nuclear physicist, but he also directed our SPS, our Students Physics Society, the undergraduate group. And while he was here, that group won, I think, even national awards for being the best program in the nation. It was incredibly active and is still active today. And a lot of the reason we are as strong as we are in that society is because of what Dr. Seagondollar did. Dr. Seagondollar also was just about the best yard sale person you'd ever want to see. He would every Saturday morning he would go out yard sailing. I used to yard sale a lot, and I would go in and I'd find something really good to buy, and it'd be marked bought by worth. He was always one step ahead of me buying these things. I once asked him what the best thing he ever bought at a yard sale was, and he said a Mercedes-Benz. So he was very good at things like that. To tell you the historical perspective, I think Professor Hubis will probably tell you a little more than I can, but I want to tell you about a book I read that has to do with this building of the bomb. It was, of course, very critical whether or not Germany was building the bomb or not. And if they were, well, one of the reasons we were building the bomb was because of the fear that Germany would develop the bomb. And there was an MIT trained physicist, had a degree in physics from MIT, who was also a CIA agent. And his name was Mo Berg, B-E-R-G, Mo Berg. And he was a brilliant man, fluent in many, many languages. And they heard that Heisenberg was going to Switzerland to go to a conference. And so they sent Berg to that conference to give a paper. He hadn't done the work, but he went to the conference. And he was to go and try to get Heisenberg off to the side somewhere, chat with him to see if he knew enough to build the bomb. And Mo Berg had a gun in his pocket. And if he knew enough, he was supposed to kill Heisenberg and leave. And Mo Berg determined that he didn't know enough and didn't kill him. That's one of the anecdotes in this. This is a biography of Mo Berg, and the book is called, I recommend it highly, called The Catcher Was a Spy. Mo Berg's cover, what his occupation was. He was the catcher for the Boston Red Sox. Very good catcher, okay? Amazing guy. There's pictures of him in the book with Franklin Delano Roosevelt, with Casey Stengel, with Heisenberg. Amazing man. But at any rate, that sets up a little bit of the history, and now that's my 5 minutes. Is Dr. Hubis next or Dr. Gould next? Dr. Hubis, can you take care of it 5 more minutes? Well, I'll go now to the parking lot to get Professor Seagondollar. And yeah.
Interesting things about solving problems was of an interest to Fermi. And Fermi, even as a student, would take on different ways in which to solve problems to get answers. If they couldn't figure out a way to do it in class, he would often find a way he could do it some other way. So for example, one day when he was just trying to find out the properties of a particular material, he said, hey, let's go down to the pool out in front. And they went down to the pool out in front and they did things like displacement and so on, found out all the properties they could about the material, and then they put it into its prospective place in the periodic table, coming up, of course, with the correct answer, but not doing any of the physics that was required. It was almost all chemistry. Well, Fermi, at the first atomic bomb explosion, had made a prediction ahead of time as to how much of an output there should be. And in order to make his measurement, when the explosion took place, he simply dropped a piece of paper and noted the path and checked it. And then when all the results were in, first of all, his simple experiment was sufficient to guarantee that his original calculation was okay, and that further calculations, much more elaborate calculations, showed him to be pretty well right on the mark. And we get a lot of good Fermi questions by following, some of the things that he used to do, and they are very, very good for classroom activities. Another, case of finding, I had a good case just a little while ago. When, see if you can slip one in before you can. Yeah, slip one in. I had another good example of Fermi that would go over well.
Okay. Well, let me give the official introduction for Worth, and then we'll lapse back to that. Normally, if the speaker's here, I wouldn't actually say when he or she was born, but since the speaker's not here, I can't actually tell you. And you could probably figure it from the fact that I was born in 1920, so we're talking about a period like 1944 to 1946. Worth got a BA degree, actually physics, math, and chemistry from Kansas State Teachers College. It became Kansas State later on in 1941. Obviously the Second World War is about to break out then. He then went to Wisconsin and was there in 1943 getting a master's degree, and it's that period right after 1943 when he went to Los Alamos. He was basically there from 44 to 46, and his reminiscences, which you're going to hear, relate to the work he was doing there during that period. Then he went back to Wisconsin, got a PhD there in 1948, then went back to the University of Kansas, and rose through the ranks there, and actually came to NC State in 1965. I don't know whether, Michael, I was out of the room, whether he mentioned that, which was only about a couple of years after the physics department was actually officially founded, split out of nuclear engineering and became its own department in the early 60s. And so Worth is basically the department head for 10 years there, for a decade, 1965 to 1975, in the very formative days of the department here. And Michael did mention the activity associated with student groups, and I think at one point Worth estimated he'd given this talk, which some version you're going to hear about, 200 or 300 times at Sigma Pi Sigma orientation events around the country. Had a tremendous record of service. He was actually national president of Sigma Pi Sigma for 6 years, and was also the leading person who kept the southeastern section of the American Physical Society going through the 80s, 70s, and 80s. In fact, the service award for the southeastern section of the American Physical Society is called the Worth Seagondollar Award, after him, because he basically ran that organization, somewhat the way John is doing it now. Now, since I gave also some kind of historical perspective at lunchtime to the graduate students, let me make a few comments about the timings of the revelations of issues here, which I think puts into perspective something one might now think about. Why did people work on this? What about all the moral qualms about these weapons of mass destruction? And if you go back to 1938, 1939, you really can read in the New York Times, in Newsweek, in all those fairly serious popular magazines, and the same in Europe, the newspapers. You can see articles about the massive destructive potential of a chain reaction. And there's all sorts of apocalyptic type stories in the newspapers, also from H.G. Wells. So it's not that this was just a kind of a few people might have known about the issues of nuclear weapons and the destructive power associated with the chain reaction. Anybody who was reading the newspaper at that time in any country in the world would have been aware of it. In fact, you can find all these things over there in the D.H. Hill Library. not only that is in the popular literature, you can find basically calculations for the critical mass of fissionable materials in the published journals. This is 1939 and 1940. It's not some deep, dark secret. It's sitting there in the French Journal of Physics, a calculation by Perrin. It's sitting there in Piles' first calculation, published, I forget, it's the Transactions of the Cambridge Philosophical Society. Absolutely in the open literature. Write down the equation which was used at Los Alamos 3 years later to calculate the critical mass. And right there in an article in a German scientific journal by Pfluger. And the only thing you didn't actually know was the numbers to put into these equations, so they're the critical mass numbers that were being talked about, sometimes 50 tons, sometimes 5 tons. But I think you may be aware that the first person to really sort of understand what it might be if you had pure metallic uranium was Piles, who wrote down that number in a British train station with Frisch of about a radius of 2 centimeters and a mass of basically a couple of kilograms. That's the calculation which triggered the article that was sent to the British government and basically initiated this whole project. But in defense of physicists at that time, I mean, if you were aware of how widely known this was, and if you were watching basically the Nazi blitzkrieg across Europe, I think you would have thought that this was a subject that should be worked on very aggressively. And I have to say, despite whatever issues you might have with nuclear weapons, it'd be hard for me now, thinking back to living at that time, not to believe that, yeah, we'd better work on this project, because if we don't, the people who discovered fission, basically the home of the leading scientists of the time, Germany, were surely working on this project and were surely going to develop these weapons. Of course, it's fascinating physics, and I think you'll get that from Worth's talk. And he's an amazing character. If he doesn't mention it in his talk, and I told people to bug him about this, make sure he talk about the flat tire. Make sure he talks about the dropped plutonium sphere. Make sure he talks about the ball-peen hammer with which he sort of fixed things up. So it's back to a time and a place of basically real hands-on physics, making things work. And it's unfortunate, obviously, the context is extremely profound, but there's no question from a physics point of view, an experimental physics point of view, must have been an exhilarating time. Now, why isn't Worth here? Well, I called him. I mean, he sent me an email message like 3 or 4 days ago, said, see you at 3:30. So I called him at 3:40, and he was just getting up and putting his jacket on. So we called him at 3:50, and he said his wife said he had been gone now for 10 minutes. So we do surely expect him to arrive on the Dan Allen parking deck and be here anytime soon.
There's a couple of stories. Most of them folks probably recognize. I think the most interesting one, which really illustrated Fermi's predilection for practical jokes and so on, was when they were under the squash courts up there at the University of Chicago and building the first pile. They were slowly putting in things, and notes were being taken and so on. And Fermi was pretty well certain that it was going to be within the next few minutes, and he said, "What? Let's break for lunch." And everybody, of course, took off for lunch, and of course, they were all there, and the only thing they really wanted to know was this going to work, or wasn't it going to work? And of course, when they came back after a regular lunch hour, of course, everything worked fine. And a bunch of, it's not email, because email was long into the future, but everything was done, of course, with messages that were all coded. Everyone had a coded name. The navigator has landed, and that was the signal that indeed fission was possible. And the program then, the Manhattan Project, started as a result of the success of that. Very expensive project, very, very rapid in the work that was done in a period of just a couple of years. If you have a chance to read, and in fact you have to read about the Manhattan Project, because there's so much physics involved. Three very well-known still today, Los Alamos, for example, worked for some time on getting things together, if you like. At Oak Ridge, one took the materials they had to make. They didn't know exactly what the bomb was going to be made of. Was it going to be a U-235 bomb? Was it going to be a plutonium-239 bomb? Were they going to be able to get the materials from an electromagnetic source? That is, were they going to be able to, as they were at the Lawrence Radiation Laboratories, going to put together enough U-235? Absolutely not. They knew that would take much, much too long. And of course, they eventually made two bombs, uranium-235 from Oak Ridge and 239 from Hanford. And welcome.
Thank you.
Okay, well, we've already had the introduction, so let's welcome Worth Seagondollar. And if we get you mic'd up here.
Yeah. I sincerely apologize for being late. There should be a good excuse for it. The excuse was just pure stupidity on my part. No excuse. As I stressed from the notice that was put up, you know that I went to Los Alamos, New Mexico, as straight from halfway through graduate school at the University of Wisconsin in 1944. In the previous decade, well, first an Englishman discovered the neutron, and an Italian had a bright idea. Let's do something really unique with this new particle for particle bombardment. Let's take an element, the top element, and bombard it with neutrons. By this time it had been established that the main thing that happened when you shot neutrons into something was the N-beta reaction. Neutrons go in, electrons go out. And when you do that, of course, that increases your positive charge by 1 point. Excuse my being out of breath. I have been traveling rather fast on the highway. Not yet. Might be a good idea later. And Fermi was successful in producing new elements. He was overly successful. He produced not just one new element, but a whole bunch of them. And the way you determine whether you've got a new element when you bombard uranium with neutrons and get beta particles out is you look for radioactivity that is different from the radioactivity of uranium-238, which is the primary isotope for uranium. And he did find new half-lives, too many of them. And he explained this by saying, well, in his bombardment of the uranium-238, he had produced some element 93. But some of this element 93 had been hit by neutrons, and this produced element 94. And some element 94 had been hit by neutrons, produced element 95, and so forth. It wasn't, there was a German woman chemist who didn't like Fermi's chemistry, and she proposed that what really had happened, that the uranium nucleus had been hit by a neutron, a compound nucleus had been formed, and the extra energy that was in that compound nucleus went into causing the thing to simply come apart. In other words, fission. And if the fission always occurred at the same ratio, well, you would have a couple of radioactive lighter elements. But there's no reason to believe that it would always come in the same, the fragments would always be the same. You could have lots of them. And this could explain what Fermi had observed. Also, about this time, no, I guess it was just a little bit later, in 1938, December of 1938, a pair of German chemists repeated Fermi's experiment, shooting neutrons into uranium and going through the chemistry to separate out the residual, the radioactive nuclei. And one of the things they found was, without any doubt whatsoever, there was a lighter element. I think it was bromine, but I won't swear to that. Without any doubt whatsoever, there was a lighter element in part of the chemical stuff that had occurred. There wasn't any question about it, that what was happening was you were getting a splitting of the nuclei of the uranium into smaller fragments. Also, you'll remember if you look at stable nuclei, you start out with light nuclei, you have the same number of protons and neutrons roughly as you go up. But as you get to heavier and heavier nuclei due to the Coulomb energy from the repulsion of the protons, you begin to find that the stable nuclei are neutron rich. They have more neutrons than they have protons. And when you get up to the very heavy stuff or into the lower end of the radioactive material, the number of neutrons is far greater than the number of protons. For instance, uranium-238, you've got 92 protons and 146 neutrons. When this splits into smaller stuff, you will get, say, some element 40 and element 52 to make up the 92 protons in the uranium. But the element 40 and the element 52 there will have many, many more neutrons. The ratio of neutrons to protons is going to be much, much higher. So there was a conclusion, and I don't know what the details of how they came to this conclusion, but it was obvious that these fragments would be intensely radioactive. These are not stable. This is not stable bromine or stable iron or anything. These elements are going to be intensely neutron rich. And somewhere along the line, a decision was made that on the average, there probably would be 3 free neutrons come out as a result of this splitting. Along this same line, probably Lisa Meitner, a woman theoretical physicist. I think she is the one who made the calculation. She calculated the Q value of the splitting of the uranium. And the answer you get is approximately 200 million electron volts. Well, is this impressive? 200 million electron volts in the palm of your hand, you wouldn't even feel. But if you think of it in terms of the dimensions of the particles which are producing this 200 MeV, and now you've got some extra neutrons, maybe you can get what we call a chain reaction. And you can get a large number of these nuclei, uranium nuclei, to split. And if so, you could be able to get a macroscopic amount of energy. Well, so what? If you take an average gasoline molecule and completely oxidize it, you get somewhere of the order of 2 or 3 electron volts. This is a big, long chain molecule. Compared to a uranium nucleus, it's a huge thing. And now then, if you want to oxidize this gasoline on a macroscopic scale, take a bucket, fill it half full of gasoline, half full of liquid oxygen, light a match, and the building probably is gone. This is first-rate rocket fuel. This is what you get with the large numbers on a macroscopic scale of something of the order of 2 or 3 electron volts. And here we're talking about 200 million electron volts per atom of uranium. And so there is a possibility of getting a chain reaction and of getting a tremendous energy release from this. This is in the December of 1938, and it's the next year that Hitler goes into Poland and World War II starts. As far as one can make the argument, this was not a particularly good time for fission to have discovered as far as the world was concerned. Soon thereafter, I think it was Norwegian underground people radioed to their counterparts in England that for some reason the Germans were modifying the output of a fertilizer plant in Norway. Well, now fertilizer is valuable stuff during wartime. You need your crops and so forth. Why then would the Germans be modifying this? And they seem to be modifying it so that they can get a small amount of stuff called heavy water out of it. And the Norwegian underground didn't know what this meant. They radioed to the British. The British talked to Americans about it. And the only thing one could think about was that somehow the only known value of heavy water at that time was to slow neutrons down. Well, why would you want to slow neutrons down? The fission cross-section, the probability of fission of the uranium, depends highly on the energy of the neutrons. There was a man who I think at the time was chairman of the physics department at Chapel Hill, or he may have gone on from there at that time. He and Niels Bohr made a calculation assuming the uranium nucleus was a liquid drop. And now then you feed energy into this drop, and how does the energy get dissipated? If it causes increased oscillation inside the liquid drop, if the oscillation gets great enough, it can separate into two fragments, like an amoeba separating. And this is the liquid drop counterpart of the fission process. And then they utilized the what information they had at that time about the fission process for uranium-235. And when you shoot neutrons into uranium, the only thing that happens is not fission. There can be other things happen, like the N-gamma reaction. The neutron goes into the nucleus, it excites it, and the excitation energy is gotten rid of by simply kicking them out electromagnetic radiation. They took what information they had and came to the conclusion, a very definite conclusion, that the amount of material which you might make a nuclear explosion of, the so-called critical mass, and I'll define this in just a moment. The critical mass for uranium-238 is infinite. The critical mass for uranium-235 was somewhere below 100 kilograms. They didn't know exactly where it was. Now, what do I mean by critical mass? Let's suppose you have a little chunk of, say, uranium-235, or later plutonium-239. You've got just a BB-sized piece of it. And you shoot a neutron in. The neutron goes in. What's the most probable thing that will happen? It will go right on through. It won't even touch any of these nuclei. If by chance that neutron happened to hit one of the, let's take uranium-235, hit a uranium-235 nucleus, and it undergoes fission, then you'll get your 200 million electron volts, which is, one of them is trivial, and you'll get about 3 extra neutrons. What's the most probable thing that will happen to these 3 extra neutrons? They'll go right on out. They'll miss also. So if you want to increase the probability that you'll get one nucleus detonating, then 3 more, you don't even need 3 more, just 1 more to continue the process. And that of the 3 neutrons from this second fission, 1 of them will cause another one. How can you increase the probability of this happening? Well, basically put more and more nuclei out there to intercept the neutrons. So if you get a big enough chunk, a neutron comes in, you get 3, and you get a fission, and three neutrons come out. One of those, or maybe more than one, causes more fission, and so forth and so forth. The minimum size that you can have in which the probability of this chain reaction being continued is what's called a critical mass. Now, critical mass, this calculation depended upon a lot of values of neutron probabilities, or neutron cross-sections, for uranium-235 and uranium-238. And after all, this is just a bunch of theorists talking about liquid drops. What you need is some uranium-235 and some uranium-238, which you can then bombard with neutrons and then measure what comes out. And you can measure the probability of the various reactions, the fission process, the gamma production, the N-alpha reaction, whatever it may be. Well, for a long time they've had things called mass spectrometers, in which you put in some material which you want to know what it is, and you ionize it. And the ions that are formed then are accelerated electrostatically and go through various electrostatic fields and magnetic fields, and they finally end up on little metal electrodes at the end of this thing. And this has been done with uranium-235 and uranium-238. And they get electrical signals for the 238 and for the 235, and they find that they've got 139 times as much uranium-238 as they have uranium-235. But nobody has produced quantities of this. What they needed were microscopic quantities of them. So mass spectrographs look like the best process. So you turn to the best mass spectrograph laboratories in the world. There are two of them. One of them's in Berlin, a fellow named Mattock, but he probably is not going to be too cooperative. The other is a guy named Al Neer at the University of Minnesota, and Neer ran his mass spectrometers on uranium 24 hours a day for 30 days, and not only got signals, but he got little microscopic quantities of uranium-238 and uranium-235. And this stuff was sent down to Los Alamos. I think Los Alamos was where this particular material was sent. And with Van de Graaff generators and other machines, neutrons were shot in and cross-sections were measured. Well, after you get a considerable amount of information of this type, you can calculate in terms of kilograms what the critical mass is for uranium-235 and for uranium-238. I remember a secret colloquium where the guy who wrote the 3 big books. What? No. The young fellow. Feynman was talking. And he says, what's going to happen if we accidentally get a critical mass of uranium-235 or plutonium-239 together? What are we going to lose? We're going to lose a beaker? We're going to lose a laboratory room? We're going to lose the eastern half of New Mexico. And at that time, really, nobody knew. Well, they had 2 Van de Graaff generators, a Cockcroft-Walton machine, and a cyclotron, all of them measuring nuclear cross-sections, and this information was being handled with theorists as quickly as they could. I remember that the man under whom I got my PhD later after the war, when you get to be my age, you have what they call senior moments. And a thing that you know perfectly well just does not click in your mind. Heinz Barschall, yeah. Heinz Barschall was putting together the first half of uranium-235. And the fellow calculation what the critical mass was, somewhere in the neighborhood of 50 kilograms, asked him, well, can you wait, let me go home at least, let me get away from this thing before you put it all together. He was confident in these calculations, but errors can occur. I had nothing to do with the measurement of the critical mass of uranium-235. I was on a 3-man team that experimentally measured the critical mass of plutonium-239. I was low man on the totem pole, and I can prove this. Al Hansen, who was the group leader for this project, had the 8 a.m. to 4 p.m. Session. The other guy, Carl Bailey, had the 4 p.m. till midnight, and I had the midnight to 8 a.m. shifts. And this proves where you stand in this particular organization, I think. We had set up equipment to measure what was called the multiplication ratio, the neutron multiplication ratio from the world supply of plutonium. Basically what we had was a radioactive source which was inside a 1-inch diameter sphere, and it was a mixture of polonium and beryllium and some other things. The neutron flux that came out of that was somewhat similar to the neutron flux that comes out from the fission process from plutonium-239. The average neutron energy is somewhere in the neighborhood of 3.2 MeV. What you want to do in a reactor is you want to slow these neutrons down to take advantage of the fact that for uranium-235, the fission process is much higher for lower energies. And this is why they put moderators in nuclear reactors, to slow the neutrons down, and when the neutrons finally hit the uranium, why they have a higher probability of causing the fission. What we had was this 1-inch sphere, and the Allied world supply of plutonium was in terms of 2 spherical hemispheres, which would fit over this 1-inch sphere. The first one was roughly 1/8 of an inch thick. Then we had 2 counters sitting out here a meter away from this thing at the center. And these were so-called long counters. These counters counted neutrons essentially independent of the neutron energy. From about 30 keV neutron energy up to 10 MeV neutron energy, the variation of efficiencies of these counters went from about 90% up to 100% and then back down to about 97%. They were the most energy insensitive neutron detectors that anybody knew of at that time. So basically our idea was we put this sphere here with nothing around it, and these 2 counters out here measure the number of neutron counts not per second, per minute. And we did this for weeks on end. We knew what that little ball was putting out. Then when the plutonium became available, the 2 plutonium hemispheres, we put them around it. Now there are two things I should mention. One is you have a guy sitting behind you. He may be in civilian clothes, he may be in military clothes. You can tell he's a plutonium guard. You can tell he has a snub-nosed .38. He doesn't have a holster. He carries it in his hand all the time. I first met him I happened to be the first in the laboratory when the stuff had arrived, and I walked over to our equipment and I heard this deep voice behind me, "Will you please stand still?" This is kind of unusual, and I'm afraid I didn't. I turned around and looked, and there's this big funnel-shaped .38 pointing at me. And the guy's an ex-professional wrestler. He doesn't need the gun, but we soon got to know each other quite well in the succeeding hours and days. His job was to see that plutonium stayed where it was, or if it went somewhere, he went with it. And you better have a good explanation for it going somewhere. We put this 1/8 inch shell around the ball and counted neutrons. What we're looking for is for an increase in the number of neutrons due to the 3 neutrons per fission that are occurring whenever a fission occurs. What we started out plotting was what we were going to call a multiplication ratio. And over here, this would be let's say the mass of the plutonium we were using. And when we start out with 0 mass, well, we get a certain, let's call this a count rate. We get a certain count rate. When we put this 1/8 inch shell across it, we got, as far as we could tell, the same count rate as we had when we had the bare ball. After we'd done about 3 days on this, it was taken away from us, taken back to a laboratory where a friend of ours was in charge of melting this down, or taking the protective cover off of it. First of all, plutonium is rather unusual material. It oxidizes rapidly. If you in an atmosphere of air, you cut a slice of it, it will turn brown and then black, and then fragments will start being there, and the fragments will blow off. And if one of these fragments, they estimated then a microgram in your lungs probably should be surgically removed. So this stuff had to be prevented from oxidizing, and it had a thin metallic coating over it. I think it was silver. I don't recall where I got this information. But at any rate, when we finished with this thin layer, it was sent back to the metallurgical laboratory, where a friend of ours, and particularly his wife was a friend of my wife's, was in charge of taking the coating off, remelting this down. Meanwhile, more plutonium had come down from Hanford, cast it into a thicker shell. And when that was done, why, it came back to us and we had some more. And maybe this time, why, we got a slightly higher count rate. And this was done over and over again. And so what we were getting was this multiplication ratio. And what we anticipated was that this would go up like this, and it would reach infinity when we got to the critical mass. Just how far we wanted to go on this was a little bit uncertain. So what we started doing was, this was the multiplication ratio that we were plotting here. We started plotting 1 over the multiplication ratio. And then what we would expect to get was this would go like this. And when the multiplication ratio was infinite, while 1 over the multiplication ratio would be 0, and we had a little more confidence of determining where that was. We did this over and over and over again as more and more plutonium came available. We got to where we estimated that we were at 98% of the critical mass. Meanwhile, our laboratory was being duplicated in a deep canyon nearby. Los Alamos is a town on a plateau, high plateau. There are some deep canyons nearby. And our equipment was being duplicated in this real deep canyon with the idea that if there was an accident, heaven forbid, that the walls of the canyon would funnel the explosion up and perhaps the town wouldn't go. We didn't do the 100% measurement. A fellow named Louis Slotin did it. I'd known Louis Slotin for quite some time because we'd been using, on different kinds of experiments, we had been sharing certain kinds of radioactive sources. I've seen Louis sit with this little 1-inch ball in his lap. I wouldn't do that, believe me. He was not really bothered by radioactivity. At any rate, his experiment completed the 100% measurement. Meanwhile, down in southern New Mexico, they were setting up a test place to set off the first plutonium device. Now, you've got this problem that you want to have a critical mass or even a supercritical mass together to get a good explosion. But you don't want to have a critical mass together before the time when you want the explosion. The first idea on this was the so-called gun assembly. And basically what they did was they took a 3-inch artillery piece, a duplicate of the German 90mm anti-aircraft gun, which put out a shell at 3,000 feet per second. The idea was you have half of your plutonium or half of your radioactive material in the end of the brass cartridge in the shell. And the other piece is out here, and you're going to shoot it in and you're going to hit it. You don't want to miss, so you screw it on the end of the gun. Somebody got the bright idea, you better evacuate the air out of the barrel, otherwise you're liable to have the thing go down and then turn around and come back. This is the basic idea of the gun assembly, and it is so simple that there really wasn't any question about whether this assembly would work or not. Unfortunately, and thank God it was realized early enough, unfortunately, when you separate plutonium, when you chemically get plutonium-239, you also get a little bit plutonium-241, which is a happy, spontaneous neutron emitter. So if you do this in the gun assembly, all the time this thing is going down here at 3,000 feet per second, part of the plutonium is emitting neutrons. What you want to do in assembly is you want to have the subcritical assembly, have them go together, and then have a trigger mechanism. And the trigger mechanism, I'm not sure of this, but I think it was another one of these 1-inch balls. But that 1-inch ball had a mixture of powdered beryllium and polonium in it. And the polonium was covered by some kind of a material so that the alpha particles that put out by the polonium would not get through the covering. But now you put one of those balls here and you slam into it and you'll mash it. Some of the polonium will lose its covering, putting out alpha particles which will hit the beryllium, which will put out a big burst of neutrons. And this, as far as I know, is the basic idea of the neutron triggers that were used both in the gun assembly and in the implosion device, which I'll talk about in a little bit. The feeling was that the number of neutrons, spontaneous neutrons coming out from the 241 were so great that the thing would probably go off before you crushed the trigger mechanism, and you would get either no real nuclear explosion or just barely a nuclear explosion. So the gun assembly was not felt suitable for plutonium. Plutonium is unusual, and it has 6 different metallic phases. I once heard Cyril Smith, the head of the metallurgical division after the war, he was asked the question, is plutonium good for anything other than nuclear processes? And he thought a bit, and then he suddenly grinned from ear to ear and says, yeah, it's good for training young metallurgists. There is nothing else that is as nasty as plutonium, and nothing else that has as many different metallic phases. Well, the basic idea was to have the plutonium in one of its metallic phases where the atoms are the farthest apart. And under these conditions, a certain size would still not be critical. But then if you do something to change, to put these atoms closer together, then you can make that assembly critical. How can you do this? Well, the idea is to use an explosion, or rather an inward directed explosion, the so-called implosion. They've known about shaped chemical charges for a long time. In the bazooka that was developed early in World War II, that was such an effective little device that sat on a soldier's shoulder, and he could kill a tank with this thing. And the tank, a rocket goes out, there is an explosive charge on the end of it, there's a contact detonator. The explosive material is designed in such a shape that the explosive shock wave goes out in a small cone, and boy, it just drills a hole through the tank and goes around and bounces around inside. This business of shaped electrical charge has been known for a long time. Basic idea was, let's have a sphere which is non-critical, and we surround it by chunks of explosive. And I think the pattern of chunks, each explosive chunk was basically the shape of the pattern on a soccer ball, as a way of getting pentagon, five-sided shapes, put them together, and it covers a sphere. And each one of these explosive devices was a shaped charge, and the direction of the explosive shock wave that comes out is not a flat plane. It is a curve, and the curve is just exactly the outer radius of the ball. So the idea was to have set all of these things off at the same time. All of these shock waves would come in and would compress this thing and get it down to where the spacing between the nuclei was small enough that it was then in a critical mass. This is a much more complicated thing. One of the reasons is, if you have a high explosive and you put a detonator in it, you detonate it, due to the high energy of the trigger, the burning rate of the explosive will be quite high at first, but as it goes out a foot or so, the burning rate of the explosive goes down, and the rate at which the explosion is propagated drops off quite rapidly. To test the instruments that were going to be used at the Alamogordo test, they had put 100 tons of high explosive, just stacked it up in boxes. And in each one of these were cubic foot boxes of high explosive, and there was a detonator in the middle. The electrical signals that would go to those detonators within a microsecond would arrive at the same time. So this 100 tons of stuff would basically explode as high explosive. It wouldn't be any low energy burning of the stuff. A friend of mine saw this thing from 9 miles away, and he said they were set off just at dawn to aid in photographic processes. And he said it looked like the sun came up halfway and then went back down. That's from 9 miles away. I know nothing about the shock wave or the sound of that particular one. I wasn't there for that one. The complications of the implosion technique, the timing, they had a heck of a time, I guess, getting the electrical signals all arrive within a microsecond on these things. There are declassified pictures of this first device. It was set off on a 100-foot high oil well tower. The whole device looks like it's about 6 feet in diameter. I know personally that the plutonium in the middle is about the size of a softball. I know this because I was in Enrico Fermi's office talking to him alone, and you may wonder why a middle graduate student is talking to Fermi in his office alone, and that's because I came back from lunch one day and a friend said, Fermi wants you to call him. And I made a remark, I suppose God's after me too, and he said, no, the man wants you to call him. So I called him, he asked me to come up. Turns out the other 2 guys that were on that experiment were already down in southern New Mexico setting up this test arrangement. And he wanted to talk to somebody who'd actually made the measurements. It took me about 5 minutes to realize that he was asking me questions that were real simple questions, basically to get me to calm down and talk intelligently. I had a tremendous respect for that man. While we were after about 15 minutes of talking, Louis Slotin shows up at the door, and he goes over on the blackboard. He writes 6 point, and I've forgotten what those 2 numbers were. I used to know them, but boy, I tried hard to forget them. There wasn't any question about it. This was the size of the sphere that, in the phase that it was, would be appropriate to be condensed and to make a critical mass of plutonium. I did have those. You can't forget numbers very easily. I would not have gone into Russia in the succeeding 5 or 6 years for any amount of love nor money. I have successfully forgotten these 2 numbers. Well, it was 6 kilograms, and it was, and that is our 98% was about the size of a softball. Well, because of the complications, maybe the implosion isn't going to work. Maybe all we'll get is a chemical explosion, in which case there's going to be $2 billion worth of plutonium scattered over the desert, and you're going to see the darndest surface mining operation you ever saw. To avoid this, they had a steel tank called Jumbo. It was about 12 feet in diameter and I think about 30, 40 feet long, and I was told that the walls of the tank were 18 inches. A few years ago, my wife and I went back down there again, and I saw the remains of Jumbo, and the walls were only about so thick. But this was a huge steel tank made in the Brooklyn Navy Yard, sent by ship down to New Orleans, then shipped by train over routes where there were strong bridges, then put on a trailer, same size trailer that you normally see for flatbed trailers pulled by trucks. Except on those there are what, 4 wheels on the back. 4 wheels per axle, 2 axles. This one have an axle and it would have all wheels. And then as close as they could get it was another axle which was all wheels and all wheels and all wheels. It was a real rugged trailer. They put it on that trailer and they pulled it out there into the New Mexico desert. They pulled it up vertical with a steel framework made of 18-inch I-beams, reinforced with 10-inch I-beams diagonally. And they used this to pull the thing up, set it down, set it in concrete. And this is what they were going to set it off in. Now all the electrical leads would have to go through insulators into it. And by, I don't know, May or June of 1945, a decision was made that the probability of problems with the lead-ins, the complications of putting it in this steel tank probably were more than the probability that the darn thing wouldn't work out in the open. So they set it off on top of this 100-foot high tower. It was set off this high because it was been already determined that if it were used against a city of Japan, it would be set off at a high altitude. And there are two reasons for this. One is if it goes off down low, it does very intense much more intense damage at the local region. If it goes up higher, the shock wave spreads out, and it still is going to just take care of everything for much larger radii. So it is a much more effective weapon in destroying the city. And the other is that undoubtedly there's going to be radioactivity. And this is a new element in warfare, and they wanted to minimize the flak that the United States was going to take due to introducing this. Well, it was set off on this 100-foot oil well tower. I and probably 200 other people were leaning up against banks that had been were part of a water runoff containment that this rancher had built. These were simply big catch basins where when it rained, which didn't very often, the water would come in there and he would have it trapped for some time. And the walls were about 4 feet thick and maybe 45-degree angle. There were two of these tanks, or two of these things, like this. And out here 9 miles away is this oil well tower. It's got a 300-watt light bulb on top of it, which you can see quite clearly from 9 miles away. I can remember leaning up against this thing and figuring, well, whatever happens is going to have to come mostly through dirt. And I was figuring the cosine of the angle with 9 miles and 4 feet. We had been warned noon before that day. There was a lunch where there were discussions afterwards about many things. Most of the things that were discussed there we already knew. For one thing, we learned that you got the worst odds in betting, assuming it was going to be the equivalent of 5,000 tons of TNT. This is what Fermi had calculated. Not Fermi, Beta had calculated. You got the worst odds there. They got us out of the bunks around 3 o'clock in the morning, and we all filed out here, and we're leaning up against this place, and the countdown began. For a long time, nothing happened. Basically, it was supposed to go off around 4 in the morning. It didn't get off until about 4:45, primarily because there were supposed to be 2 B-29 superfortresses within about 40 miles of it to take pictures from there. It turns out that there were storm clouds up there, and there were U.S. Army Air Force regulations that you do not take B-29s into storm clouds. And over the FM radio system, which had loudspeakers everywhere, we could hear this Air Force colonel who was in charge of the 2 planes explaining to this civilian that he didn't know, but the civilian was very calm and confident and seemed to have considerable authority. The civilian was urging him to get closer, and he was telling him he couldn't do that because of the Army regulations, Army Air Force regulations, and it was a rather interesting dialogue, and this went on for about 30-40 minutes, till finally the planes got not to where they were supposed to be, but one of them was close enough that Oppenheimer decided that we should go ahead with the countdown. We've been warned at this luncheon before. There was a Colonel Stafford Warren who was a head medical man for the Manhattan District. He said, a number of things you should be aware of tomorrow morning. One of them is that it may go off and the radioactive dust cloud, the wind may shift. The radioactive dust cloud may come directly towards us, in which case there will be plenty of alarm over the public address system, and they will tell you whether to go to parking lot A or parking lot B. If it says go to A, go to A, do not go to B. There are different roads going out of them, and anybody going to the wrong one trying to drive a vehicle out will be shot. So this explains this. It may be that the radioactive dust cloud will blow in the direction it's supposed to towards a certain group of mountains, and there'll be no danger from that. But there still could be real danger to the retina of your eye if you're looking at it. He strongly recommended the strongest sunglasses you could get your hands on, and you'd be looking in the opposite direction, and from the reflected light you decide when and if you want to turn around and look. Well, we'd thought about this at Los Alamos before we drove down, and the result, I had a case of acetylene torch welder's goggles, and the more he talked, the dimmer those goggles got. I noticed they had a welding shop, and that afternoon I went over and traded the whole box of goggles for 5 pieces of blue glass that go in electric arc welder's hood. And 5 of us took 1 foot square pieces of cardboard, cut a little rectangle in it, and scotch taped the blue over it. And this was our sunglasses, which we thought were pretty good. We had looked at a 100-watt old-fashioned carbon light bulb the night before, and you could barely see the outline of the carbon filament. These were dark pieces. Well, when the countdown came, I, as was told, was looking in the opposite direction, and I counted 1,001, 1,002, 1,015, turned around to look. My first reaction was, you darn fool, you forgot the blue glass. I was looking through the blue glass, but there wasn't any trace of blue what I was seeing. It was just pure white hell out there. The ball of fire, if this is the ground, the ball of fire was about its own diameter above the earth, and this goes on up. There are clouds up ahead. The clouds just parted like this, and this goes on through. By far, the most impressive thing was the terrific amount of light that was there. It was like looking into a photographer's flashbulb, but that's concentrated. And I swear, when I looked through that blue glass, that light was everywhere. The sound was real heavy rolling thunder. Now, I've come from the Midwest, and I've heard a lot of thunder. Around here, you don't get so much, but out there, you get some real blasts of thunder out there. What I heard there at Alamogordo was not as loud as some of the thunder I've heard in Kansas. But if you stop and think about it, you're all familiar with this trick of counting seconds after you see lightning, and it takes 5 seconds for the sound to travel a mile, and you seldom have heard thunder that has come from over a mile. And this had come a minimum of 9 miles. So undoubtedly it was very, very noisy there. The shock wave, I don't know whether it got there before the sound wave did or not. It was sort of like standing in an open door and near an open door, and somebody slams the door, and just a big puff of air went by. Following, a couple of hours after the explosion, there were 2 tanks that were supposed to go out and see what the damage had been. One of them had only a minimum amount of lead on it, had periscopes, several periscopes, so they could look out. It had radiation measuring devices on the outside and on the inside. Fermi and a crew of others were inside this one, and it left first. And he was going to go as far as he could, observing what had happened. I was standing by a loudspeaker by a guy named William Penny, who was a British demolition expert who was later knighted in England. One of the most important pieces of equipment out there as far as Fermi was concerned was we had some wooden boxes that were 1 meter cubes, and they're glued together except for one side is open. Then there's a piece of plywood goes down the middle, another piece of plywood here, 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 and so forth. And you see you're getting smaller and smaller areas. And they had glued heavy paper over these boxes. And the idea being that if the pressure above atmospheric got to be only a very small amount, why this one would break. If it was more than that, why this one would break. More than that, this one would break. And these things were facing the road where the tank was going to go down. And we heard Fermi radioing back what he was seeing. When he was 2 miles away, he radioed that the overpressure, the pressure of the blast over atmospheric, was 5 pounds per square inch. And this English demolition expert says, oh my God. He just wasn't aware that such pressures could be developed at such distances. I'll wind this up by saying that a friend of mine had the job of putting up instruments on meteorological balloons close to the oil well tower. These instruments were vaporized, there's no question about it. But then maybe that just, anyhow, what he did was he talked somebody into giving him a Jeep and letting him go back down there and look for these things. And I guess I was the first one he ran into after he'd gotten permission to do it. Did I want to go along? Sure, I wanted to go along. So I got to go down there about 30 days after the blast. What I saw was pretty horrifying. This heavy-duty 100-foot-high oil well tower was gone. It was vaporized. There still were some fragments of it down near the ground embedded in concrete. The crater itself was, I was amazed at how small, I'm going on over, Chris.
Well, finish up your story.
All right. I was amazed at how small it was. What was really horrifying was outside of the crater itself. The desert had been melted. It was now a green glass, very highly radioactive green glass. We brought back a bucket full of it, with it as far away from it as it could be in the vehicle. This is what I saw after something that was later described as 17 kilotons of explosion. In the business of fusion explosions, the first one was out on an island in the Pacific. It was in a building. It was not up on a 100-foot high tower. I've seen a photograph of the equipment. It looked like maybe it was 20 feet above the concrete slab. The crater that was caused by it was somewhat larger. This was on an island that was 3/4 of a mile long and 1 3/4 miles long. After the explosion, the island was gone. Average depth of the ocean there was 175 feet. So this gives you a comparison between atomic weapons and fusion weapons. I'll conclude with one thing I've just got to bring up. I teach a 1-hour science thing out at Springmore twice a month. And one of the topics that a friend of mine brought up was tactical nuclear weapons. If you're on the internet, you want to look up tactical nuclear weapons and get ready for something extremely unpleasant. Apparently, the Americans built something like 18,000 tactical nuclear weapons in the with energy ranges, say, in the neighborhood of 1 kiloton to 10 kilotons. These were to be used against the Russian tanks when they came into East Germany. The Germans learned that we were making these things, and some Russian general in charge of this wanted to make Russian ones. Well, how much material would he need? Well, he wanted 100 tons of plutonium and 30 tons of uranium-235. And out of this, apparently, he made 40,000 tactical nuclear weapons. Now, as you are all aware, there's a lot of going back and forth, diplomatic going back and forth between the Russians and the United States with regard to strategic nuclear weapons, the city busters. In terms of tactical nuclear weapons, they have tried to do this and they have gotten nowhere. Right now, there is no agreement whatsoever to do about tactical nuclear weapons. It was reported last December in an Islamic newspaper that Al-Qaeda has had several tactical nuclear weapons for the past 6 years. There's a lot of other nasty stuff on the internet about tactical nuclear weapons, and I recommend you read it. Thanks. Yes, ma'am.
I'm asking you the question my students asked me that I didn't know the answer to. They want to know how radioactive is the New Mexico desert right now.
Let me phrase it this way. I have, and I didn't have time to pick them up to get down here because I was late. I have some samples of that bucket of stuff that we took. And it's in a glass container. About in the 1950s, I took a Geiger counter and compared the radioactivity of several chunks of this stuff about this size with the radioactivity of my wristwatch. The Geiger counter could pick up the radioactivity of my wristwatch. It could pick up nothing from this stuff. So I think the answer is, and I can say this with real firm feeling, that there is no radioactivity of the desert down there now. Now, 30 days afterwards, it was hot as could be. We went in a Jeep, and in 10 minutes, with radiation measurement devices, the Jeep driver says, "I'm leaving. You can stay if you want to," because his instrument had read 15R at that time. We piled into the Jeep and got out of there. So the answer is, as far as anything down there now, there's nothing. And also, I've been down there myself about 3 years ago, and there isn't anything there, any radioactivity there. Well, thank you very much. Oh, good. Boy, I apologize for being late. I just simply forgot it.
No, I should have told you. I suddenly was thinking about it.
It would have helped. Hi, stranger. Even with this, I recognize you. Fine, fine. And relatively speaking.
We got you on tape.